For most of human history, the speed of light was not a barrier. It was not even a concept. People looked at the sun rising over distant mountains, watched lightning tear across storm clouds, and assumed light simply appeared. Instantaneously. Effortlessly, without delay. The universe seemed immediate. If a star shone in the night sky, then surely its light existed there in that same moment. If a distant fire burned on a hilltop, then its glow reached your eyes without hesitation. Reality appeared connected by invisible threads of immediacy, and for thousands of years, nobody questioned it. That assumption survived civilizations. It passed through ancient Greece, imperial China, medieval Europe, and the scientific revolution itself. Even as humanity learned that Earth orbited the sun and discovered laws governing planets' motion and gravity, light remained strangely mysterious. It illuminated everything, yet nobody knew what it truly was. Then something unexpected happened. In the 17th century, a Danish astronomer named Ole Rømer began studying one of Jupiter's moons. At first glance, his observations seemed unrelated to any grand mystery. He was simply tracking eclipses. The moon disappeared behind Jupiter. It reappeared, then disappeared again. A predictable celestial clock. Except the clock was misbehaving. Sometimes the eclipses arrived early. Sometimes they arrived late. The pattern refused to cooperate. Astronomers assumed errors were responsible. Perhaps the observations were inaccurate. Perhaps the calculations were wrong. But the discrepancies persisted again and again. Rømer noticed something strange. When Earth moved farther from Jupiter, the eclipses appeared delayed. When Earth moved closer, they appeared sooner. The difference was small, yet it was consistent. The light itself seemed to require time to travel. Not much time, but time nonetheless. The implication was astonishing. Light was not instantaneous. It moved. It crossed space. It possessed speed, a finite speed. For the first time in history, humanity glimpsed something hidden beneath ordinary experience. Reality contained latency. The universe had transmission delays. Every observation was slightly outdated. Every image was a message arriving from the past. The stars above were not present. They were memories. At the time, few people appreciated how profound this discovery truly was. After all, what difference did it make? Light was still extraordinarily fast. Its delay remained invisible in everyday life. The world around us appeared unchanged. But beneath that appearance, something fundamental had shifted. A silent crack had formed in humanity's understanding of reality. Because once light possessed a finite speed, a new question emerged. Could anything move faster? At first, the question seemed harmless. Why shouldn't something travel faster? Horses were faster than walking. Ships were faster than swimming. Cannons were faster than arrows. Every apparent limit in history had eventually been surpassed. Human progress often looked like a series of broken barriers. What reason existed to believe light would be different? No one knew. And for centuries, the mystery remained unresolved. Meanwhile, scientists continued investigating the nature of light itself. The deeper they looked, the stranger it became. Sometimes light behaved like a wave. Sometimes it behaved like a particle. Sometimes it seemed to be both simultaneously. It slipped through experiments like a suspect changing disguises. Every answer generated new questions. Every breakthrough exposed another layer of uncertainty. Then came the 19th century. Electricity and magnetism were finally being understood. Equations emerged that described invisible forces spreading through space. Among them were the revolutionary equations of James Clerk Maxwell. When Maxwell examined his equations closely, he discovered something extraordinary. The mathematics predicted waves, not ocean waves, not sound waves, electromagnetic waves. And these waves moved at a specific speed. A speed determined entirely by the structure of nature itself. When Maxwell calculated the value, he found something shocking. The speed matched the measured speed of light, almost perfectly. Light was not merely illumination. Light was an electromagnetic phenomenon, a ripple moving through reality. For many scientists, the mystery seemed solved. Case closed. Humanity finally understood light, or so it appeared. This would become the first false ending, because solving the nature of light accidentally created a much larger problem, a problem buried inside Maxwell's equations a problem nobody could explain. Imagine standing inside a train moving across a landscape. If you throw a ball forward, an observer on the ground measures the train's speed plus the ball's speed. The velocities combine naturally. This principle worked everywhere. Carts, ships, bullets, planets. Motion seemed relative, straightforward, predictable, but light refused to cooperate. Maxwell's equations suggested something impossible. They implied that every observer would measure exactly the same speed of light, always, regardless of their own motion. That could not be correct, or so everyone thought, because common sense demanded otherwise. If you chased light, shouldn't it appear slower? If you ran toward it, shouldn't it appear faster? The logic felt unavoidable, yet the equations insisted otherwise. The conflict lingered like an unresolved clue at a crime scene. Scientists searched desperately for explanations. Perhaps light traveled through an invisible medium, an unseen substance filling all space. They called it the luminiferous ether. The ether became a comforting solution. If light behaved like a wave, surely it needed something to wave through. Water carries ocean waves. Air carries sound waves. Maybe space contained its own hidden ocean, an invisible cosmic substance. If the ether existed, Earth's motion through it should be detectable. Experiments were designed. Measurements were taken. Expectations were high. Then came the result nobody expected. The ether wasn't there, or at least nobody could find it. One of the most famous experiments in scientific history searched for evidence of Earth's motion through this invisible medium. Nothing appeared. No trace. No signal. No hidden ocean. The universe remained stubbornly silent. And suddenly, physicists faced a mystery far more troubling than before. If the ether didn't exist, why did light behave as though its speed never changed? What mechanism enforced such a bizarre rule? What hidden principle lurked beneath reality? The answer would arrive from an unlikely source, a young patent clerk, a man who was not trying to solve faster than light travel, a man who was merely trying to understand light itself. His name was Albert Einstein, and what he uncovered would transform the speed of light from an interesting measurement into the most important boundary in the universe. But the real mystery was only beginning. By the beginning of the 20th century, physics appeared nearly complete. The major mysteries seemed solved. The planets obeyed gravity. Electricity obeyed Maxwell's equations. Light had been identified as an electromagnetic wave. Many scientists believed only a few minor details remained. Small adjustments, tiny refinements. The foundations appeared secure. Yet beneath those foundations, hidden cracks were spreading. The failure to detect the ether had become impossible to ignore. Experiment after experiment returned the same unsettling conclusion. No matter how carefully scientists searched, the invisible medium that was supposed to carry light refused to appear. The evidence accumulated like footprints leading nowhere, and that was deeply troubling, because if light truly moved through empty space, then something about motion itself had to be wrong. The old assumptions no longer fit the observations. Reality was behaving differently than common sense predicted. Into this confusion stepped a young physicist with a dangerous habit. He trusted evidence more than intuition. Instead of asking how light fit into existing ideas, he asked a more uncomfortable question. What if the existing ideas were wrong? The question sounds simple. It wasn't. Because the existing ideas had survived centuries. They seemed obvious. They matched everyday experience. When you walk forward inside a moving train, your speed combines with the train's speed. When you throw a stone from a moving wagon, its motion adds to the wagon's motion. Everything behaved this way. Everything except light. Einstein wondered what would happen if the speed of light truly remained constant for everyone. Not approximately constant. Exactly constant for every observer, under all circumstances, no exceptions. At first glance, the proposal sounded absurd. Imagine chasing a beam of light. Common sense suggests you should gain on it. Perhaps not much, but at least a little. Yet Maxwell's equations said otherwise. The light would still race away at exactly the same speed, no matter how fast you pursued it. The consequence was astonishing. If light speed never changed, then something else had to change instead. something humanity had always considered fixed, something even more fundamental: time, space, or both. This was the moment the investigation took an unexpected turn. Scientists had been studying light. Instead, they found themselves investigating reality itself. Einstein's breakthrough emerged from a thought experiment, not a laboratory, not a telescope. Just imagination, guided by logic. Suppose two observers measure the same event. One remains stationary. The other moves at enormous speed. If both must observe light travelling at the same velocity, then their measurements of distance and time cannot agree. Reality would need to adjust. The universe would compensate. Space would contract. Time would stretch. The faster an observer moved, the more dramatic these distortions would become. At first, these ideas seemed impossible, almost mystical. Yet the mathematics worked, and more importantly, experiments eventually confirmed it. The evidence kept appearing again and again and again. Time itself was not universal. That statement remains difficult to absorb even today. We experience time as something absolute, a shared river carrying everyone forward together. Yet relativity revealed a different picture. Time behaves more like a landscape. Observers moving through that landscape can follow different paths. Their clocks can disagree. Their measurements can differ. Both can be correct. This discovery represented one of the greatest perspective shifts in human history, but it also created a new mystery. If time and space can change, what exactly remains fixed? The answer pointed back to light. Everything else could vary. Distances, durations, Massachusetts, energy. But the speed of light remained unchanged, almost as if the universe were built around protecting it. Imagine a city whose entire road network rearranges itself whenever someone tries to break a speed limit. The roads shorten, the clocks slow, the landscape shifts. Yet the limit itself never changes. That is essentially what relativity describes. The universe bends its measurements before allowing light speed to be violated. And as physicists explored this strange architecture, they uncovered another surprise. The closer an object approached light speed, the harder it became to accelerate further. Energy continued pouring into the object, but instead of increasing speed, normally the object resisted, like pushing a vehicle toward an invisible wall. The wall could not be seen, yet its presence became unmistakable. Each additional increase required more energy than the last, more effort, more power, more resources. As though reality were raising the price, then raising it again, then again. The closer one came to light speed, the steeper the cost became. The mathematics painted a remarkable picture. Reaching the speed of light would require infinite energy, not enormous energy. Infinite energy, an amount that can never be supplied. No civilization, no machine, no star, no galaxy. Nothing in the known universe possesses infinite energy. The implication was devastating. Light speed was not merely difficult to reach, it was unreachable, at least for anything possessing mass. This was the second apparent solution to the mystery. The case seemed closed. Nothing can exceed light speed, because nothing can even reach it. Problem solved. Except it wasn't, because the solution raised a far larger question. Why? Why should reality contain such a barrier at all? Why this speed? Why not another value? Why does nature seem organized around protecting it? The answer was unclear, and strange clues began appearing elsewhere. Consider the sun. The light striking your face today left the solar surface roughly 8 minutes ago. That fact alone feels remarkable. You never see the sun as it is. You see it as it was. The same is true for everything. The moon appears about 1 second in the past. Jupiter appears tens of minutes in the past. Nearby stars appear years in the past. Distant galaxies appear millions of years in the past. Some of the ancient galaxies observed by the James Webb Space Telescope appear billions of years in the past. Astronomy became an unexpected form of archaeology. Telescopes do not merely observe distance, they observe time. Every image is a fossil. Every photon carries a historical record. Every observation is delayed by the finite speed of light. And that delay creates a curious consequence. The universe we experience is not the universe as it exists right now. It is the universe's memory, a vast archive of ancient signals arriving from every direction. This realization transformed the speed of light from a technical detail into something much larger. It governed information, knowledge. Cause and effect, the structure of observable reality itself. And that is where the investigation became truly unsettling. Because if light speed controls information, then what happens if something moves faster? Could information arrive before it is sent? Could effects appear before causes? Could the future influence the past? These questions sounded like science fiction, yet buried inside relativity were mathematical hints suggesting that the consequences might be far stranger than anyone imagined. The barrier was no longer simply about motion. It was becoming a mystery about time. And the next clue would lead scientists toward a possibility so disturbing that many hoped it did not exist at all. Particles that might already live beyond the speed of light. Particles that, if real, would force reality to rewrite its own history. What physicists found next would prove even stranger. The idea arrived almost by accident, not from a telescope, not from a particle accelerator, not from a strange signal emerging from deep space. It emerged from mathematics. And throughout the history of science, some of the most unsettling discoveries have begun exactly that way. Before Neptune was ever seen, equations hinted at its existence. Before antimatter was detected, mathematics suggested it should be there. Again and again, reality revealed a strange habit. Sometimes the equations knew things before the universe did, or at least before humans did. That possibility became especially unsettling once physicists began examining the consequences of relativity more carefully. Einstein's theory had successfully explained why objects with mass could never reach light speed. The barrier appeared absolute, solid, unbreakable, case closed. Or so it seemed. Then someone asked a dangerous question. What if the barrier wasn't a wall? What if it was a boundary separating two different kinds of existence? The distinction mattered enormously. Imagine standing at the shoreline of an ocean. You cannot walk directly across the water, but that does not mean nothing exists on the other side. Perhaps the speed of light functioned similarly. Perhaps ordinary matter occupied one side of the boundary, and something else occupied the other. The mathematics allowed for an intriguing possibility. Particles traveling slower than light could never accelerate enough to reach light speed, but hypothetical particles already moving faster than light might never need to cross the barrier at all. They would simply exist beyond it, always, forever. On the opposite side, this strange possibility eventually received a name: tachyons. The word came from the Greek term for swift, yet there was nothing simple about them. At first glance, tachyons appeared to offer a solution. Perhaps faster-than-light motion wasn't impossible. Perhaps humanity had simply been looking at the problem incorrectly. Instead of accelerating ordinary matter beyond light speed, maybe nature already contained entities that lived there naturally. For a moment, the mystery seemed closer to resolution. This would become another false ending. Because the deeper physicists investigated tachyons, the stranger the situation became. One clue emerged immediately. According to the equations, tachyons behaved in reverse compared to normal matter. Ordinary objects require increasing energy to move faster. Tachyons would do the opposite. The more energy they lost, the faster they would travel. The less energy they possessed, the closer they would approach infinite velocity. That alone sounded bizarre, but it was merely the beginning. Another consequence proved far more disturbing. Imagine watching a movie. A glass falls from a table. It shatters on the floor. Cause. Then effect. The sequence feels obvious, natural, unavoidable. Reality appears organized around this order. Events occur, consequences follow. But tachyons threatened that structure, because once faster-than-light motion enters the picture, the order of events begins to depend on perspective. For one observer, event A might happen before event B. For another observer moving differently, event B could appear to occur first. This was not merely a disagreement about timing, it was a disagreement about causality itself. The universe's most fundamental rule seemed vulnerable, and that was alarming because causality is not just another scientific principle. It is the foundation upon which all experience rests. Every memory, every decision, every chain of events. Everything depends on causes preceding effects. Remove that structure, and reality begins to unravel. Physicists soon encountered an astonishing implication. A tachyon-based message might theoretically arrive before it was sent. Pause for a moment and visualize that. Imagine receiving a letter tomorrow warning you not to send the very message that produced the warning. Which event happens first? Which event causes the other? The question appears simple, yet the answer becomes surprisingly difficult. This thought experiment eventually evolved into a collection of famous paradoxes. The most well-known involved time travel. A traveller journeys into the past, changes history, prevents their own journey. The cause eliminates the effect that created it. The logical loop collapses. Reality becomes trapped in contradiction. For decades, physicists wrestled with these implications. Many suspected the paradoxes themselves constituted evidence. Not evidence that faster-than-light motion existed. Evidence that it could not. Almost as though the universe were warning us. Proceed further, and logic breaks. Cross this boundary, and contradictions emerge. Reality seemed remarkably protective of causality, yet uncertainty remained, because mathematics alone cannot settle every mystery. Nature gets the final vote. The question therefore became practical. If tachyons existed, could scientists find them? Could experiments reveal traces of these hypothetical particles? The search began. Researchers examined cosmic rays, particle collisions, high-energy interactions, exotic physical processes. The effort spanned decades. Every possible clue attracted attention. Every anomaly inspired speculation, and every hint eventually faded. No tachyon ever appeared. Not conclusively, not reproducibly, not convincingly. Again and again the evidence refused to cooperate. The particles remained elusive. Ghosts haunting equations rather than laboratories. Yet the mystery survived. Because absence of evidence is not always evidence of absence. Especially in physics. History contains many examples of entities that remained invisible for generations before technology finally revealed them. Neutrinos were once hypothetical. Black holes were once controversial. Gravitational waves spent a century waiting for confirmation. Perhaps tachyons belonged to the same category. Or perhaps they did not exist at all. Nobody knew. And the uncertainty created an uncomfortable situation. The most obvious path beyond light speed remained purely theoretical, an intriguing possibility, nothing more. Meanwhile, another puzzle was quietly emerging, one that did not involve hypothetical particles, one that involved the universe itself. Astronomers had begun observing distant galaxies with increasing precision. As measurements improved, a remarkable pattern emerged. The cosmos was not static. It was changing, expanding, growing larger over time. That discovery alone transformed humanity's understanding of existence. But hidden inside the expansion was a clue so strange that many scientists initially struggled to accept it. Certain galaxies appeared to be receding from us at extraordinary speeds, enormous speeds, and some calculations suggested something almost impossible. The most distant regions of the universe seemed to be moving away faster than light itself. At first glance, this looked like a direct violation of Einstein's cosmic speed limit. Had the universe discovered a loophole? Had nature secretly broken its own rule? Or had physicists misunderstood the barrier all along? The answer seemed tantalizingly close. After decades of mystery, perhaps the first genuine example of faster-than-light motion had finally been found. But what investigators uncovered next would transform the mystery into something far larger than particles, galaxies, or even motion itself. Because the real culprit might not be matter. It might not be energy. It might not even be light. It might be space itself. And that possibility changed everything. For centuries, space was treated as a stage, a silent backdrop upon which the drama of the universe unfolded. Stars moved through it, planets drifted within it, galaxies occupied it, but space itself seemed passive, empty, featureless. a vast container holding everything that existed. Even after Einstein revolutionized physics, many people continued imagining space this way. It felt intuitive. After all, when you look into the night sky, you do not see space moving. You see objects moving through space. The distinction appears obvious, yet some of the greatest mysteries in science emerge precisely when something obvious turns out to be wrong, and this was one of them. The clue first appeared in the early 20th century. Astronomers had begun measuring distant galaxies with unprecedented accuracy. Powerful telescopes revealed an astonishing universe filled with island-like collections of stars, scattered across unimaginable distances. At first, scientists assumed these galaxies occupied a static cosmos. The universe simply existed, unchanging, eternal. That assumption felt natural. Many philosophers had embraced it for centuries. Even Einstein initially preferred it. A static universe appeared stable, comfortable, reasonable. Then the observations arrived, and everything changed. One astronomer in particular, Edwin Hubble, noticed something remarkable. The farther away a galaxy appeared, the faster it seemed to be moving away from us. Not occasionally, consistently. The pattern emerged everywhere scientists looked. Distant galaxies were receding. The universe was expanding. At first, the discovery seemed straightforward. Galaxies moving apart. Mystery solved. Except it wasn't. Because the deeper researchers investigated, the stranger the expansion became. Imagine placing dots on the surface of a balloon. As the balloon inflates, each dot moves away from every other dot. No single dot sits at the center. The surface itself expands. The dots are not actively traveling across the rubber. The rubber is stretching beneath them. This analogy became one of the most important conceptual tools in cosmology, because it suggested something radical. Perhaps galaxies were not moving through space in the traditional sense. Perhaps space itself was expanding. The distinction sounds subtle. It isn't. It changes everything. If galaxies merely traveled through space, Einstein's speed limit would apply directly. Nothing could exceed the speed of light. Case closed. But if space itself expanded, the situation became far more complicated. The speed limit governs motion through spacetime. It says nothing about spacetime itself changing. That loophole would prove extraordinarily important. As measurements improved, astronomers uncovered a startling fact. Some galaxies appeared so distant that the expansion between us and them exceeded the speed of light, not slightly, by enormous amounts. Entire regions of the cosmos seemed to be receding faster than Einstein's limit. At first glance, this appeared catastrophic. Had relativity failed? Had the universe broken its own rules? Had physicists misunderstood the most important theory of the 20th century? The mystery deepened rapidly, because the observations were real. The data refused to disappear. Again and again, the numbers pointed toward the same conclusion. Parts of the universe were effectively moving away faster than light. For a moment, it seemed the case was finally solved. Perhaps faster than light motion already existed. Perhaps humanity had simply overlooked it. This was yet another false ending, because the truth proved even stranger. The galaxies themselves were not violating relativity. They were not accelerating through space beyond light speed. Instead, the distance between galaxies increased because the fabric of space expanded. The galaxies behaved more like passengers standing on a moving walkway than runners breaking a speed record. The walkway created the separation, not the passengers. This distinction preserved Einstein's theory, but it also introduced a new possibility. If space could expand faster than light, what else might space-time be capable of doing? That question lingered quietly. Then cosmologists looked deeper into the past, much deeper. Beyond galaxies, beyond stars, beyond the formation of atoms, toward the beginning of everything. The story led back nearly 14 billion years to the event we call the Big Bang. Popular culture often portrays the Big Bang as an explosion, a cosmic detonation occurring at a specific location. But modern cosmology describes something more subtle and far stranger. The Big Bang was not an explosion inside space. It was the expansion of space itself, everywhere. Simultaneously, the distinction matters enormously because it means the universe did not emerge into pre-existing emptiness. Space itself was part of the event. The stage and the actors appeared together. Yet even this picture contained unresolved clues. When scientists examined the early universe carefully, they encountered puzzles that seemed impossible to explain. One mystery involved temperature. Regions of the cosmos separated by immense distances possessed nearly identical temperatures. That sounds harmless. It wasn't. Because those regions should never have communicated with one another. Light simply did not have enough time. Signals could not travel between them. Information could not be exchanged. And yet they appeared remarkably similar. Why? How? What hidden process connected them? The problem became known as the horizon problem, and for years it resisted explanation. Then a revolutionary idea emerged, an idea so bold that many researchers initially struggled to accept it. What if the infant universe experienced an episode of unimaginably rapid expansion? Not ordinary expansion, extreme expansion, a brief period during which space itself grew faster than light, far faster. In a tiny fraction of a second, microscopic regions could become cosmically vast. Areas once close together would be carried far apart. The temperature mystery would disappear. The evidence would suddenly make sense. This concept became known as cosmic inflation. And if inflation was correct, then something extraordinary happened near the dawn of existence. The universe itself expanded faster than light. Not metaphorically, not approximately, literally. For a brief moment, reality outran the very limit that later seemed absolute. The implication was staggering. The speed of light barrier might not be as simple as humanity once imagined. It remained fundamental. Yet the universe appeared capable of sidestepping it under certain conditions, almost as if nature knew hidden pathways inaccessible to ordinary matter. And that realization raised a disturbing question. If space-time itself can exceed light speed, if the early universe already did so, then could advanced civilizations eventually learn to manipulate space the same way? Could the barrier that traps every spacecraft be circumvented rather than crossed? Could the solution to faster-than-light travel lie not in moving faster, but in moving space? The idea sounded almost magical, yet buried inside Einstein's equations were clues suggesting it might not be impossible, and those clues would eventually inspire one of the most controversial concepts in modern physics. A machine that does not travel through space. A machine that carries space with it. What scientists discovered next would blur the line between science fiction and legitimate theory in ways few people expected. The idea did not emerge from dreamers. It did not begin in science fiction novels. It did not originate in Hollywood. That is what makes the story so unusual, because one of the most famous concepts associated with faster-than-light travel was born not from fantasy, but from Einstein's own equations. And for a brief moment, it appeared that the mystery might finally have an answer. The question was deceptively simple. If nothing can travel through space faster than light, what happens if you stop trying to move through space altogether? The distinction sounds trivial. It isn't. Imagine standing on an airport moving walkway. You can remain completely motionless relative to the walkway itself, yet you still travel across the terminal. The floor carries you. You are transported without actively crossing the distance. Now imagine replacing the walkway with space-time. Instead of accelerating a spacecraft through the universe, what if the universe itself could be manipulated? What if space could move? The idea lingered on the edges of theoretical physics for decades. Most researchers dismissed it. Not because it violated Einstein's theory, but because it seemed hopelessly impractical. Then something unexpected happened. In 1994, physicist Miguel Alcubierre published a paper that attracted immediate attention. The mathematics suggested a startling possibility. Einstein's equations appeared to permit a configuration of spacetime now known as the Alcubierre drive. At first glance, the concept seemed impossible. The deeper scientists examined it, however, the stranger it became. Because technically the spacecraft inside such a warp bubble would never exceed the speed of light, not even once. Inside the bubble, the ship would remain relatively stationary. Its local physics would behave normally. no forbidden acceleration, no violation of relativity. Instead, the surrounding space-time would do all the work. Space in front of the vessel would contract, space behind it would expand. The ship would ride this distortion like a surfer riding a wave. The destination would be brought closer. The origin would be pushed farther away. Distance itself would change, and from an outside perspective, the spacecraft could appear to travel faster than light, much faster. Perhaps dramatically faster, perhaps fast enough to cross interstellar distances in days rather than millennia. The implications were extraordinary. For the first time, faster-than-light travel seemed to possess a mathematically respectable framework. Not proof, not engineering, but a legitimate theoretical pathway. The scientific community reacted cautiously. Excitement spread. So did skepticism, because history had taught physicists an important lesson. When something appears too convenient, hidden complications usually exist, and complications soon emerged, many of them. The first problem involved energy, specifically a type of energy nobody had ever observed in usable quantities. The equation suggested that a warp bubble required negative energy. This phrase often creates confusion. Negative energy does not simply mean less energy. It refers to conditions that behave in profoundly unusual ways. Imagine a hill and a valley. Ordinary energy resembles climbing upward. Negative energy resembles digging below the ground itself. The concept is mathematically meaningful, yet nature appears reluctant to provide it. Certain quantum phenomena hint at its existence. Tiny effects observed in laboratory experiments suggest negative energy may occasionally appear on microscopic scales, but a warp drive required vastly larger amounts. At first, calculations seemed almost comical. Some estimates implied energy comparable to entire stars. Others suggested amounts exceeding the mass energy of planets. The dream of practical, faster-than-light travel suddenly looked much less convincing. Yet researchers continued investigating, and that persistence uncovered something fascinating. The required energy estimates began changing. Refined models reduced the demands. New mathematical approaches produced smaller requirements, not small enough, but smaller. The mystery refused to die. Each apparent dead end generated another question. Could future discoveries reveal new mechanisms? Could unknown forms of matter exist? Could advanced civilizations exploit aspects of physics humanity has not yet discovered? No one knew. Then another complication emerged, and this one proved even more troubling. Suppose a warp drive could be built. Suppose the energy problem were somehow solved. Would the bubble actually be controllable? The answer was unclear. Some analyses suggested a disturbing possibility. Once a warp bubble formed, communicating with its leading edge might become impossible. Signals could struggle to reach the region controlling the distortion. The spacecraft could effectively lose steering capability. Imagine constructing a ship capable of crossing oceans, then discovering nobody can control the rudder. The vessel exists, but navigation does not. The mystery deepened further, because every attempt to solve one problem revealed another waiting beneath it, like layers of buried architecture emerging during an archaeological excavation. One hidden chamber led to the next. One answer uncovered a larger uncertainty. Then came another surprise. Researchers examining warp drive physics noticed something peculiar. Certain calculations hinted at enormous concentrations of radiation surrounding the bubble, potentially catastrophic concentrations. A successful journey might deliver its passengers safely to their destination, only to release devastating bursts of energy upon arrival. The very mechanism enabling faster-than-light travel could become dangerous, perhaps lethal. Again, the mystery seemed solved. Again, the answer appeared negative. Warp drives were impossible. Case closed. Yet once more, reality refused to provide closure. New papers appeared. Alternative models emerged. Objections were challenged. Solutions were proposed. The debate continued. And that persistence revealed something important. The true significance of warp drive research was never the engineering. It was the realization that Einstein's theory itself contained hidden possibilities. The equations were more flexible than many scientists had imagined. Spacetime was not merely a passive arena. It possessed structure, dynamics, potential behaviors far stranger than anyone expected. The investigation had now moved beyond particles, beyond galaxies, beyond simple motion. The focus was shifting toward the fabric of reality itself. And that shift exposed another ancient possibility lurking within Einstein's equations. A possibility even stranger than warp bubbles. A possibility involving shortcuts through the universe, not by carrying space, not by expanding space, but by folding space, like bending a sheet of paper until two distant points touch. The concept had existed for nearly a century. Most scientists treated it cautiously. Some considered it impossible. Others suspected it might reveal something profound about the hidden architecture of the cosmos. They were called wormholes, and if they exist, they may represent the most direct route beyond the speed of light ever imagined. But the real mystery was only beginning. Long before anyone spoke of warp drives, another possibility had already been hiding inside Einstein's equations. It appeared quietly, almost accidentally, a mathematical curiosity. The kind of strange solution many physicists initially assume cannot exist in the real universe. History is full of such ideas. Most disappear, a few survive. And occasionally, one evolves into something that changes our understanding of reality. Wormholes belonged to that category. At first glance, the concept seems almost childish. Fold a sheet of paper. Mark two distant points. Push the points together. A path that once required crossing the entire page now requires only a tiny step. The analogy is simple enough for a child to understand. Yet buried beneath it lies one of the deepest mysteries in theoretical physics, because space-time itself might possess a similar flexibility. Distance may not be as absolute as it appears. The clue emerged from studies of gravity. Einstein had transformed gravity from a force into something stranger. Mass and energy distort space-time. Objects follow those distortions. Planets orbit stars not because they are being pulled through empty space, but because space-time itself becomes curved. Imagine placing a heavy ball on a stretched fabric. The surface bends. Smaller objects roll along the resulting contours. The analogy is imperfect, but it captures the essence. Gravity is geometry, and if space-time can bend, a troubling question follows. Can it bend enough to connect distant regions directly? Can separate parts of the universe touch? The mathematics suggested they might. Certain solutions to Einstein's equations described tunnels, bridges, passages linking different regions of space-time. These theoretical structures eventually became known as wormholes. The name itself evokes something ancient and hidden. A worm tunneling through an apple, a shortcut invisible from the surface. The comparison is remarkably effective. A traveller crossing normal space might require thousands of years to reach a destination. A traveller using a wormhole could potentially arrive almost instantly, not because they moved faster than light, because they travelled a shorter route. This distinction became critically important. Just as warp drives attempted to manipulate space-time rather than violate relativity, wormholes appeared to exploit geometry itself. The speed limit remained intact, yet the journey changed completely. For a moment, the mystery once again seemed close to resolution. Perhaps this was the answer. Perhaps faster-than-light travel never required breaking Einstein's rules. Perhaps the universe already contained hidden pathways, ancient corridors threading through space-time, invisible roads waiting to be discovered. It was an enticing possibility. Too enticing, because deeper analysis uncovered severe problems. The first challenge involved stability. Many theoretical wormholes collapsed almost instantly. They pinched shut before anything could cross. Imagine discovering a bridge that appears only for a fraction of a second. Technically useful, practically worthless. Researchers searched for mechanisms capable of holding wormholes open, and once again, they encountered a familiar obstacle: negative energy. The same exotic ingredient haunting warp drive research appeared here as well. Without it, many wormholes seemed doomed to collapse. Reality appeared reluctant to permit shortcuts, almost as though space-time possessed its own immune system. Whenever physicists identified a route beyond ordinary limitations, another restriction emerged, another lock, another hidden safeguard. The universe seemed determined to protect something. But what? The answer remained elusive. Then the mystery became even stranger, because wormholes introduced a consequence far more unsettling than rapid travel: time travel. The connection was not immediately obvious. After all, Wormholes were supposed to connect locations, not eras, places, not histories. Yet relativity transformed the situation. Imagine two ends of a wormhole. One remains stationary. The other experiences extreme motion, or perhaps intense gravity. According to Einstein's theory, time flows differently under such conditions. Clocks diverge. Aging differs. Moments separate. When the two ends reconnect, they may no longer share the same temporal reference. One entrance could effectively become linked to the past relative to the other. The implication was astonishing. A sufficiently manipulated wormhole might function as a time machine, not metaphorically, literally. And that possibility sent shockwaves through theoretical physics, because every paradox discussed in connection with tachyons suddenly reappeared. Perhaps even more dramatically. Messages could arrive before they were sent. Events could influence their own causes. The logical structure of reality seemed vulnerable once again. This pattern was becoming impossible to ignore. Every path beyond light speed eventually converged on the same obstacle: causality. Again and again, like a warning sign appearing on every road. You may manipulate space. You may exploit geometry. You may search for loopholes. But eventually, you encountered time, and time refuses to cooperate. Some physicists began suspecting that this was not an accident. Perhaps causality was more fundamental than light speed itself. Perhaps the speed limit existed because it protected the sequence of events, the order of cause and effect, the coherence of reality. This suspicion inspired one of the most influential ideas in modern theoretical physics, a concept proposed by physicist Stephen Hawking. He called it the chronology protection conjecture. The name sounds technical. Its meaning is simple. Nature may actively prevent time travel, not through engineering difficulties, not through practical limitations, but through deeper laws woven into reality itself. According to this idea, the universe protects its own history. Attempts to create paradoxes trigger physical processes that destroy the conditions necessary for paradoxes to occur. Reality enforces consistency. The mechanism remains uncertain, the evidence incomplete. Yet the concept explains something intriguing: why every faster-than-light proposal eventually encounters profound obstacles. Why shortcuts become unstable. Why paradoxes emerge. Why solutions collapse into larger mysteries. The pattern begins to look intentional, not intentionally designed, but structurally inevitable, like rivers flowing downhill because the landscape demands it. Then another clue appeared, one that would transform the entire investigation, because physicists studying quantum mechanics discovered something even stranger than wormholes, something apparently capable of connecting distant locations instantly. No tunnels. No warp bubbles, no exotic spacecraft, just particles. Ordinary-looking particles behaving in ways that seemed impossible. For decades, some researchers believed they had finally found the first genuine violation of Einstein's cosmic speed limit. The phenomenon became famous, misunderstood, controversial, and deeply mysterious. It was called quantum entanglement, and at first glance it appeared to change everything. If wormholes felt like hidden tunnels beneath reality, quantum entanglement felt even stranger, because tunnels at least belong to the world of ordinary intuition. You can imagine a tunnel. You can visualize a shortcut. You can picture two distant places connected by a passage. Entanglement offers no such comfort. It does not resemble anything from everyday experience. It does not behave like a machine, or a road, or a signal. Instead, it behaves like a clue from a universe operating according to rules we do not fully understand. The mystery first emerged from the foundations of quantum mechanics, a theory so successful that modern civilization depends upon it. Computers, lasers, semiconductors, medical imaging. Entire industries rest upon quantum physics. Yet despite its extraordinary predictive power, physicists still debate what quantum mechanics actually means. That uncertainty alone is remarkable. Imagine using a machine every day while admitting you do not completely understand why it works. Quantum mechanics occupies that strange territory. Its equations succeed. Its interpretation remains unresolved. and nowhere is this tension more apparent than in entanglement. The phenomenon begins innocently enough. Two particles interact. Their properties become linked. Afterward, measuring one particle immediately determines information about the other, even if the particles are separated by enormous distances. At first, scientists assumed there must be some hidden explanation, a secret mechanism, an invisible connection, some buried variable carrying information between them. The alternative seemed absurd. How could two distant particles remain coordinated? How could nature preserve such correlations across space? The question bothered many physicists, including Einstein himself. In fact, Einstein disliked entanglement so intensely that he famously referred to it as spooky action at a distance. The phrase endured because it captured the discomfort perfectly. Something about entanglement felt wrong, incomplete, suspicious, as though an important piece of the puzzle remained hidden. Einstein believed a deeper theory would eventually restore common sense. A more complete framework would explain the mystery. The strange correlations would disappear. Reality would become intuitive again. That expectation seemed reasonable. For decades, many physicists agreed. Then experiments began arriving, and they told a different story. Increasingly sophisticated tests examined entangled particles under carefully controlled conditions. Again and again, the results supported quantum mechanics. Again and again, hidden variable explanations struggled. Again and again, reality behaved exactly as the strange theory predicted. The evidence accumulated relentlessly. One experiment became 10. 10 became hundreds. The pattern persisted. Entanglement was real. The universe truly behaved this way. Particles separated by vast distances displayed correlations that seemed impossible to explain through ordinary communication. This discovery created a wave of excitement, and almost immediately a familiar idea emerged. Had faster-than-light communication finally been discovered? The possibility appeared irresistible. If measuring one particle instantly influences another, surely information is traveling faster than light. Surely Einstein's barrier had finally fallen. For a moment, the mystery seemed solved. The universe itself appeared to be demonstrating faster-than-light connections. This would become one of the most famous false endings in modern science. Because the deeper researchers investigated, the stranger the truth became. The particles were indeed correlated. The correlations appeared instantaneously, yet no usable information travelled between them. That distinction proved crucial. Imagine two sealed boxes. Each contains a card. One card is red, the other is blue. The cards were placed there before the boxes were separated. You carry one box to another galaxy. A friend keeps the other. When your friend opens their box and discovers a red card, they instantly know yours contains blue. Information has been revealed, but nothing actually travelled between the boxes. The result was determined beforehand. Entanglement is not exactly like this analogy, yet it highlights an important principle. Correlations do not automatically imply communication, and quantum mechanics exploits that distinction in astonishing ways. The universe seems capable of creating relationships that transcend ordinary notions of separation. Yet those relationships stubbornly refuse to become faster-than-light messages. Every attempt to extract a practical communication system fails. Nature permits the mystery, but not the shortcut. This pattern was becoming familiar. Again and again, physicists approached the speed of light barrier from different directions. Tachyons, warp drives, wormholes, entanglement. Each appeared promising. Each seemed poised to unlock the mystery, and each eventually encountered hidden restrictions. The barrier remained intact. Yet something interesting was happening. The repeated failures were teaching scientists something profound. The speed limit might not merely constrain motion, it might define the architecture of reality itself. That realization inspired a new generation of questions. Perhaps researchers had been asking the wrong thing. Instead of asking how to exceed light speed, perhaps they should ask why the universe enforces it so carefully. What is being protected? What hidden structure depends upon the limit? The clues pointed toward information. Again and again, information appeared at the center of the mystery. Light carries information. Causality organizes information. Entanglement constrains information. The deeper investigators looked, the more reality resembled a vast informational network. A cosmic system governing what can be known, when it can be known, and by whom. Then another astonishing astonishing development appeared, one emerging not from quantum experiments alone, but from studies of black holes. The darkest objects in the universe were revealing unexpected clues. For decades, black holes had been viewed primarily as gravitational prisons, regions where escape becomes impossible, the ultimate cosmic traps. Yet as physicists studied them more carefully, they uncovered something deeply unsettling. Black holes seemed connected to information in ways nobody anticipated. In fact, some researchers began suspecting that space-time itself might emerge from informational relationships. The implication was staggering. If true, space could be less fundamental than information. Distance could be secondary. Geometry could arise from deeper connections hidden beneath reality. Suddenly, the investigation expanded again. The mystery was no longer merely about moving beyond light speed. It was becoming a mystery about why space exists at all. And if space is not fundamental, then the meaning of distance, and perhaps even the meaning of the speed limit itself, may be very different from what humanity has assumed. What physicists uncovered next would force them to reconsider one of the oldest assumptions in science. The assumption that space is real in the way we think it is. The answer seemed obvious. It wasn't. For most of human history, space seemed undeniable. You could point toward a distant mountain, walk toward it, measure the distance. The separation felt real, concrete, obvious. Even after the scientific revolution transformed humanity's understanding of nature, space retained its status as one of reality's unquestioned foundations. Objects existed within it. Events occurred inside it. The universe occupied it. Space appeared fundamental. End of discussion. Yet some of the most important discoveries in science begin when a supposedly obvious truth becomes uncertain. And during the late 20th century, an unexpected suspicion emerged among theoretical physicists. What if space is not fundamental at all? What if it is something else, something deeper, something emergent? The proposal sounded radical, perhaps even absurd. Yet clues kept appearing from unexpected directions. One of those clues came from black holes. At first glance, black holes seem unrelated to faster-than-light travel. They are regions where gravity becomes so intense that even light cannot escape. The ultimate cosmic prisons, the exact opposite of unrestricted motion. But black holes have a habit of transforming every mystery they touch, and this mystery was no exception. The story began with a troubling question. Imagine throwing information into a black hole. A book, a computer, an entire library. The black hole absorbs everything. Eventually, according to quantum theory, the black hole evaporates through a process known as Hawking radiation. The black hole disappears. So, what happens to the information? Where does it go? At first, the answer seemed obvious. It vanishes. The black hole destroys it. Case closed. Except quantum mechanics refuses to allow that conclusion. The laws governing quantum systems strongly suggest that information cannot simply disappear. The universe appears to preserve it, always. That conflict produced one of the greatest scientific debates of the modern era, the black hole information paradox. For decades, physicists argued fiercely. Some believed information was destroyed. Others insisted it survived. The disagreement was not merely technical. It struck at the foundations of reality. Because if information can vanish, then quantum theory itself may be incomplete. If information survives, then black holes must behave in ways we do not yet understand. Either possibility carried enormous implications, and hidden inside the debate was a clue pointing towards something astonishing. Researchers noticed that the amount of information associated with a black hole seemed related not to its volume, but to its surface area. This result was deeply strange. Imagine discovering that everything inside a house could be fully described by information written on its walls, not the rooms, not the interior, just the surface. The idea sounded impossible, yet the mathematics kept pointing in that direction. The implication grew increasingly difficult to ignore. Perhaps information behaves differently than expected. Perhaps reality itself behaves differently than expected. This line of thinking eventually contributed to one of the most extraordinary concepts in theoretical physics, the holographic principle. The name sounds futuristic. Its implications are even stranger. According to the holographic principle, the three-dimensional universe we experience may emerge from information encoded on a lower dimensional boundary. A useful analogy involves a hologram. A flat surface can generate the appearance of depth. Three-dimensional structure emerges from two-dimensional information. The holographic principle suggests something similarly profound may occur within the cosmos. Reality could be more like a projection than we ever imagined. The idea remains controversial, incomplete, actively investigated. Yet many physicists take it seriously because it repeatedly appears in successful mathematical frameworks. And if the concept contains even a grain of truth, then a remarkable possibility emerges. Space itself may not be fundamental. It may arise from informational relationships hidden beneath ordinary experience. Suddenly, the investigation changed direction once again, because if space emerges from deeper structures, then distance becomes less absolute. Separation becomes less fundamental. The speed of light barrier begins to look different. Imagine characters living inside a digital simulation. From their perspective, distance appears real. Travel requires time. Movement obeys rules. Yet beneath their world lies computational infrastructure connecting everything simultaneously. The analogy is imperfect, but it captures an important shift in perspective. Perhaps space-time is not the deepest layer of reality. Perhaps it is an emergent phenomenon generated by something more fundamental, something hidden. Something currently beyond direct observation. Then another clue appeared. This one involved quantum entanglement itself. Researchers studying connections between entanglement and space-time geometry noticed something astonishing. The mathematics suggested that entanglement might actually help create space-time, not merely operate within space-time, create it. The idea sounded almost unbelievable. Particles becoming connected through entanglement could correspond to geometric connections within space-time. Some physicists even propose provocative slogans. Space is built from entanglement. Geometry emerges from information. Distance arises from relationships. These statements remain speculative, yet they reflect a growing suspicion. The universe may be stitched together by informational structures more fundamental than space itself. If true, the consequences are staggering, because the speed of light governs motion through space-time. But what if space-time is not fundamental? What if the barrier emerges alongside the geometry it constrains? Then exceeding light speed may resemble asking how to exceed the limits of a map while ignoring the terrain beneath it. The question itself may be incomplete. The deeper reality may operate according to entirely different principles. This realization represented another false ending. The mystery seemed to dissolve. Perhaps faster-than-light travel is irrelevant because space itself is not fundamental. Problem solved. Except the solution created even larger questions. If space-time emerges from something deeper, what is that deeper thing? Information. Quantum states. Mathematics. Something humanity has not yet imagined. Nobody knows. And the uncertainty continues expanding, like a doorway opening into darkness. Each answer reveals another mystery waiting beyond it. Meanwhile, astronomers studying the observable universe or uncovering additional clues. The cosmos itself appeared to contain boundaries, invisible horizons beyond which information could never reach us, regions permanently hidden from observation. No matter how long humanity waits, no matter how advanced future civilizations become, entire portions of reality may remain forever inaccessible. And that possibility raised a disturbing question. Perhaps the greatest mystery surrounding faster-than-light travel is not whether it can be achieved. Perhaps the greater mystery is what remains hidden because it cannot. The investigation was no longer about crossing a boundary. It was becoming an investigation into the limits of knowledge itself. And the next discovery would make those limits impossible to ignore. There is a horizon surrounding you right now. You cannot see it. You cannot touch it. You do not notice its presence when you look at the stars, yet it exists, a boundary woven into the structure of the cosmos itself. Beyond that boundary lie regions of reality that are permanently unreachable, not merely difficult to reach, not merely far away, fundamentally inaccessible. This realization emerged gradually. Like many profound discoveries, it began with something that appeared harmless. Astronomers were measuring the age of the universe, the expansion rate of space, the distances to galaxies. Each improvement sharpened humanity's picture of the cosmos, and each improvement revealed something unexpected. The universe is finite in age, approximately 13.8 billion years old. That fact immediately imposes a limit. Light requires time to travel. Therefore, there are regions whose signals have not yet had enough time to reach us. Simple enough. At first, scientists assumed this limitation was temporary. Given sufficient time, more of the universe would eventually become visible. The cosmic curtain would slowly withdraw. The hidden regions would reveal themselves. A reasonable assumption. But reality proved less accommodating, because the universe was not merely expanding. The expansion itself was accelerating. That discovery arrived near the end of the 20th century, and shocked the scientific community. Galaxies were not simply drifting apart. The separation was speeding up. Some unknown process was pushing the cosmos outward. The evidence accumulated from multiple observations. Distant supernovae, large-scale cosmic structure, measurements of ancient radiation left behind by the Big Bang. Again and again, the same conclusion emerged. Something was driving accelerated expansion. Scientists eventually gave it a name: dark energy. The label sounds dramatic. In truth, it represents ignorance more than understanding. Dark energy is not a complete explanation. It is a placeholder, a way of saying that something appears to be accelerating cosmic expansion, but we do not yet know what it is. The name identifies the mystery. It does not solve it. And hidden inside that mystery was another clue about the speed of light. As expansion accelerates, distant galaxies recede faster and faster. Eventually, some become permanently unreachable. Not because spacecraft lack sufficient power, not because technology remains primitive, because space-time itself carries those regions away faster than any signal can cross the growing separation. Imagine swimming toward a shoreline while a river continuously widens beneath you. No matter how hard you swim, the destination retreats even faster. The effort becomes meaningless. This is essentially what happens on cosmic scales. The universe creates horizons, not physical walls, informational walls, boundaries beyond which influence cannot propagate. The implications are extraordinary. There are galaxies whose future light will never reach Earth, ever. Not in 1 trillion years, not in 1 quadrillion years, never. The information remains permanently isolated. Entire histories unfolding beyond our reach. Entire civilizations, if any exist, forever disconnected. Entire regions of reality separated by cosmic expansion. The observable universe, therefore, is not the entire universe. It is merely the portion accessible to us. A local neighborhood, a visible island surrounded by unseen territory. And nobody knows how much lies beyond it. This realization transformed the investigation once again. Because humanity had spent centuries imagining the speed of light barrier as a transportation problem. How do we travel faster? How do we cross greater distances? How do we reach the stars? But cosmic horizons reveal a deeper consequence. The barrier limits knowledge itself. It determines what can be observed, what can be known, what can be influenced. The speed of light is not merely a speed limit. It is an epistemological limit, a boundary governing information. That distinction may be the most important clue of all. Then another unsettling thought emerged. Suppose some civilization somewhere has already solved faster than light travel. Suppose warp drives exist. Suppose wormholes exist. Suppose the universe contains mechanisms humanity has not yet discovered. Would cosmic horizons still matter? The answer is not obvious. Some theoretical models suggest horizons remain significant. Others hint at loopholes. The mathematics becomes increasingly uncertain, and uncertainty breeds mystery, because every attempt to peer beyond observable limits confronts the same problem. Evidence disappears. Observation ends. Inference takes over. Scientists find themselves investigating shadows, traces, indirect clues. The hidden architecture of reality reveals itself only partially. Like a buried city, visible through fragments protruding from sand, you know something larger exists, but the complete structure remains concealed. This situation has occurred before, again and again, throughout history. Ancient astronomers believed the solar system was the universe. Later generations discovered the Milky Way, then other galaxies, then billions of galaxies. Each horizon eventually expanded. Each apparent boundary concealed larger realities. Naturally, this history inspires optimism. Perhaps current limits will also fall. Perhaps future discoveries will reveal new layers beyond today's understanding. Perhaps. Yet there is an important difference. Previous horizons were technological. The current horizon may be physical. The distinction matters enormously. A technological limit can often be overcome. A physical limit may be woven into reality itself. And that possibility raises a disturbing question. What if the speed of light is not merely a feature of our universe? What if it is a consequence of deeper laws that any universe capable of supporting causality, information, and structure must obey? In other words, what if the barrier is not accidental? What if it is necessary? The idea began attracting attention among physicists, not because it could be proven, but because so many independent clues seem to converge toward it. Relativity, quantum theory, causality, information, cosmic horizons. Again and again the same pattern appeared. The speed limit looked less like an arbitrary rule and more like a foundational principle, a load-bearing beam supporting reality itself. Remove it and the structure begins to wobble. Remove it entirely and perhaps the structure collapses. Yet certainty remained elusive, because physics has a habit of surprising those who become too confident. And just when the mystery seemed to be approaching resolution, another set of observations complicated everything. Astronomers began noticing phenomena that appeared to move faster than light. Not theoretically, not mathematically, actually observed. Jets erupting from distant galaxies, explosions spanning enormous distances, structures apparently outrunning light itself. For a brief moment it looked as though nature had finally betrayed Einstein's limit. But appearances, as physicists would discover, can be deeply deceptive, and the next clue would reveal how the universe sometimes creates illusions more convincing than reality itself. The photographs looked impossible. Long, narrow jets of matter erupted from the centers of distant galaxies, stretching across space for thousands of light years. They emerged from regions surrounding supermassive black holes, some containing billions of times the mass of the Sun. These were among the most energetic structures in the known universe, cosmic lighthouses visible across enormous distances. And when astronomers measured their apparent motion, something extraordinary appeared. Parts of these jets seemed to be moving faster than light, not slightly faster. Sometimes several times faster. The observations were real. The calculations appeared correct. And for a brief, electrifying moment, it seemed as though the mystery might finally be solved. Nature itself appeared to be violating Einstein's cosmic speed limit. No exotic particles, no speculative wormholes, no hypothetical warp drives, just direct observation, evidence, reality caught in the act. The scientific community reacted cautiously. Experience had taught researchers an important lesson. Extraordinary claims often conceal ordinary explanations. Yet the data refused to disappear. Again and again the same pattern emerged. Certain jets displayed what became known as superluminal motion, motion apparently exceeding the speed of light. The term itself carried an air of revelation. Perhaps after a century of debate, humanity had finally discovered genuine faster-than-light phenomena. But the deeper investigators looked, the stranger the situation became, because the observations contained a subtle clue. The objects were not simply moving across the sky, they were moving toward Earth at nearly the same time. That distinction turned out to be crucial. Imagine a fast airplane flying almost directly toward you. Each second the aircraft travels a significant distance. Yet because much of that motion occurs along your line of sight, the visual geometry becomes deceptive. Now scale that situation to relativistic speeds, close to light speed, across intergalactic distances. Suddenly, strange optical effects begin to emerge. The light emitted from different positions along the jet reaches Earth at unexpectedly similar times. Events that were separated in space become compressed in observation. The result creates an illusion, a remarkably convincing illusion. The jet appears to outrun light. In reality, it does not. The apparent violation exists only from a particular observational perspective, like a shadow racing across a landscape faster than the object creating it, or a laser spot sweeping across the moon faster than light, without any physical object actually making the journey. The discovery was both disappointing and fascinating. Disappointing because another apparent loophole had vanished. Fascinating because it revealed how easily intuition can be deceived when dealing with relativistic phenomena. The universe was once again teaching the same lesson. Reality is stranger than common sense, and common sense often fails at cosmic scales. This pattern had become impossible to ignore. Every time scientists believed they had discovered a way beyond the speed limit, the mystery transformed, not solved. Transformed. A new layer appeared. A deeper complication emerged. Another hidden mechanism revealed itself. Yet something valuable emerged from these failures. Each false lead exposed another aspect of how the universe works. Each dead end illuminated the structure of reality more clearly. And that structure seemed increasingly centered around information, not matter, not energy. Information. The clue became especially clear when physicists examined what the speed of light actually represents. Most people think of it as the speed of illumination, the speed at which light travels. Technically correct, but incomplete. The deeper interpretation is far more profound. The speed of light is the maximum speed at which information can propagate through space-time. That distinction changes everything, because information lies at the heart of every physical process, every force. Every interaction, every cause and effect relationship. When the sun emits light, information about the sun travels outward. When gravity influences a planet, information propagates through space-time. When particles interact, information is exchanged. Reality itself depends upon informational transfer, and the speed of light governs that transfer. This realization transformed the barrier from a transportation problem into something deeper. Imagine a vast communication network. Every event in the universe acts like a message. Every interaction resembles data transmission. The speed limit defines how quickly those messages can spread. Without it, causality becomes unstable. Effects can outrun causes. Histories become ambiguous. The architecture begins to fracture. Suddenly, Einstein's limit looked less like a restriction and more like infrastructure, a foundational component necessary for coherence, like the frame supporting a building. You rarely notice it, yet remove it, and everything changes. Then came another perspective shift, one that emerged from studies of the early universe. Researchers began asking a provocative question. What if the speed of light has not always been constant? The idea sounded almost heretical. After all, relativity treats the speed of light as fundamental, immutable, one of the defining features of reality. Yet certain cosmological puzzles inspired speculation. Perhaps conditions in the infant universe differed radically from those observed today. Perhaps the laws themselves evolved. Some theoretical models explored varying speed of light scenarios. The proposals remained controversial. Most physicists remained skeptical. The evidence was inconclusive. Yet the very existence of such discussions revealed something important. Humanity still does not fully understand why the speed limit possesses its specific value. Approximately 299,792 kilometers per second. Why that number? Why not faster? Why not slower? Why any limit at all? The deeper researchers investigated, the more mysterious the constant became. It appeared everywhere. Electromagnetism, relativity, particle physics, cosmology. The value seemed woven throughout the fabric of reality, like a recurring symbol appearing in every chapter of an unfinished manuscript. A clue, a signature, evidence of deeper structure, and that structure was about to become even stranger, because the investigation was approaching one of the most dramatic discoveries in modern cosmology. A discovery suggesting that the universe itself may have once expanded so rapidly that ordinary notions of distance and causality temporarily lost their meaning. The event occurred less than a fraction of a second after the Big Bang. Yet its consequences still surround us today, hidden in the oldest light in existence, buried in the structure of the cosmos, waiting to reveal what may be the closest thing science has ever found to a genuine faster-than-light event. What happened next changed everything. If you could travel backward through time and witness the first moments of the universe, you would not find stars. You would not find galaxies. You would not find planets' atoms or even light moving freely through space. You would find something far stranger, a reality so extreme that familiar concepts begin to lose meaning. Temperature becomes almost unimaginable. Density rises beyond ordinary intuition. The entire observable universe exists within a volume smaller than a grain of dust, perhaps much smaller, and hidden within those earliest moments lies one of the most important clues in the entire investigation. Because long before galaxies drifted apart, long before black holes formed, long before the first stars illuminated the darkness, something happened that still puzzles cosmologists today. The universe appears to have expanded at a rate that seems impossible. The evidence for this extraordinary event emerged gradually. Astronomers studying the cosmos noticed several troubling anomalies. Individually, each anomaly looked manageable. Together, they formed a mystery. One involved the remarkable uniformity of the universe. Wherever scientists looked, the cosmos appeared surprisingly similar. The temperature of the ancient radiation left behind by the Big Bang, the cosmic microwave background, was nearly identical across enormous distances. That sounds harmless. It wasn't, because those regions should never have communicated with one another. According to ordinary expansion, there simply wasn't enough time. Light travelling at its maximum speed could not have crossed the required distances. Information should not have been exchanged, and yet the temperatures matched with astonishing precision. Imagine walking into a stadium containing billions of people. Every person flips a coin. Every coin lands the same way. Possible. Technically. Plausible. Not remotely. The universe displayed a similar improbability. Something appeared to have coordinated regions that should have remained isolated. But how? That question lingered for years. Then another puzzle emerged. The geometry of the universe appeared strangely balanced. Measurements suggested that space-time was remarkably flat on cosmic scales. Not exactly flat, but extraordinarily close. Again, this required explanation. Why should the cosmos possess such delicate balance? What mechanism created it? The clues accumulated, the mystery deepened, and eventually a bold proposal emerged. The idea came from physicist Alan Guth, and was later refined by many others. The proposal was both elegant and radical. Perhaps the infant universe experienced an episode of explosive expansion, a brief but extraordinary event, an expansion so violent that it dwarfed everything that came afterward. A fraction of a second after the Big Bang, space itself may have ballooned by an incomprehensible factor. Regions once microscopic became astronomical. Tiny patches became vast cosmic domains. The implications were profound. Areas that had once been close enough to exchange information would later appear impossibly distant. The temperature puzzle vanished. The geometric puzzle vanished. Several unrelated mysteries suddenly acquired a common explanation. This success made inflation one of the most influential ideas in modern cosmology. Yet hidden within its success was something deeply unsettling. The expansion occurred faster than light, much faster, not because matter exceeded Einstein's limit, not because information outran causality, because space-time itself expanded. The distinction once again proved crucial. And yet the psychological impact remained enormous. For generations, people had treated the speed of light as the ultimate barrier. Now, cosmologists were proposing that the universe itself had effectively outrun that barrier during its infancy. Reality had already done something that sounded impossible. The cosmos had performed a feat no spacecraft could achieve, and it had done so before the first stars existed. For a moment, the mystery seemed close to resolution. Perhaps inflation explained everything. Perhaps the universe simply possesses the ability to expand faster than light under extreme conditions. Case closed. This would become another false ending, because inflation solved certain mysteries while creating others. As often happens in science, the answer generated larger questions. What caused inflation? Nobody knows. What triggered it? Nobody knows. Why did it stop? Nobody knows. What physical field powered it? The evidence remains incomplete. The event explains much. Its origin remains hidden. Imagine arriving at an ancient city buried beneath desert sands. You uncover roads, buildings, walls, evidence of sophisticated planning. Clearly, something remarkable happened there, yet the identity of the builders remains unknown. Inflation occupies a similar position within cosmology. Its fingerprints appear everywhere. Its ultimate cause remains elusive. Then the mystery grew even larger, because some versions of inflation lead to a startling possibility. The expansion may never have completely ended. Not everywhere. In certain regions, inflation could continue indefinitely. New universes might constantly emerge. Bubble universes, pocket universes, entire cosmic domains separated by expanding spacetime, each potentially possessing different conditions, different histories, perhaps even different physical constants. The idea remains speculative, yet it emerges naturally from some mathematical models, and if true, it transforms the investigation completely. The question is no longer what lies beyond the speed of light. The question becomes what lies beyond our universe. The scale of the mystery expands once again. Planet, star, galaxy, universe. Now, beyond universe, the pattern continues. Every apparent answer reveals a larger horizon. Every solved mystery uncovers deeper uncertainty, and this uncertainty carries an important lesson. The speed of light barrier may not merely define motion within our universe. It may define the limits of communication between entire cosmic regions, entire realities, entire histories. Then another realization emerged, one even more profound. Physicists began noticing that every route toward faster-than-light travel eventually collided with a common obstacle. Not energy, not engineering, not technology, time. Again and again, time stood in the way. The barrier seemed less concerned with distance than chronology, less concerned with speed than causality, almost as though reality's deepest priority was preserving the order of events. That suspicion would soon become the central focus of the investigation, because understanding the speed of light might ultimately require understanding something even more fundamental. Not space, not motion, not matter, time itself. And what scientists discovered when they followed that clue would force them to reconsider the very meaning of past, present, and future. Most people think the great mystery surrounding faster-than-light travel is distance. The stars are too far away. Galaxies are too vast. The universe is too large. From that perspective, the speed of light appears to be a transportation problem, a frustrating obstacle standing between humanity and the cosmos. But by now, the investigation has uncovered a different pattern. Again and again, every path beyond light speed has collided with something else, something more fundamental: time. The deeper physicists explored the mystery, the more the barrier appeared to protect chronology rather than distance. And that realization led to an uncomfortable question. What exactly is time? At first glance, the answer seems obvious. Time is what clocks measure. Seconds pass, minutes accumulate, days become years, the future becomes the present becomes the past. Simple, natural, self-evident. Yet history repeatedly demonstrates that seemingly obvious concepts often conceal profound mysteries, and time may be the greatest example of all. Long before Einstein, scientists treated time as universal, a cosmic river flowing identically for everyone, the same everywhere, the same always, whether on Earth or among the stars, whether standing still or racing through space. Time remained absolute. Then relativity shattered that assumption. Clocks moving at different speeds no longer agreed. Observers experiencing different gravitational conditions no longer shared the same passage of time. The river fractured. Multiple timelines emerged, all equally real, all equally valid. This discovery alone was extraordinary, but hidden within it was a clue even stranger. Physics seemed remarkably indifferent to the direction of time. Many fundamental equations work equally well forward or backward. A collision recorded on video often looks plausible when reversed. Particles interact according to mathematical rules that frequently display symmetry between past and future. This creates a mystery. If the laws themselves are largely indifferent to temporal direction, Why does time appear to flow one way? Why do we remember the past, but not the future? Why does a broken glass remain broken instead of spontaneously reassembling? Why does entropy increase? Why does history possess an arrow? The question sounds unrelated to faster-than-light travel. It isn't, because causality depends upon temporal order. Causes precede effects. The past influences the future, not the other way round. Every paradox generated by faster-than-light motion ultimately threatens that sequence, and that makes the arrow of time critically important. Imagine a library in which every book constantly rearranges its pages. Narratives collapse. Stories lose coherence. Meaning disappears. Causality serves a similar function within reality. It organizes events into comprehensible sequences. Without it, the universe becomes logically unstable. This is why physicists pay such close attention whenever a theory appears to permit influences traveling faster than light. The concern is not merely speed. The concern is chronology, preserving coherent history. And remarkably, nature seems to share that concern. Every faster-than-light proposal examined so far encounters barriers related to temporal consistency. Tachyons create paradoxes. Wormholes threaten chronology. Warp drives generate causal complications. The pattern repeats relentlessly, as though reality possesses hidden safeguards. Then another perspective emerged, one inspired by an unexpected source: black holes. Again, these enigmatic objects kept appearing at the center of fundamental mysteries: information, entropy, quantum gravity, now time itself. Researchers studying black holes noticed something remarkable. The event horizon behaves in curious ways with respect to causality. Information crossing the horizon appears trapped. Future and past become intertwined in unusual manners. Classical intuitions begin to fail. The closer physicists looked, the more they suspected that time might not be fundamental either. Just as some theories suggest space emerges from deeper structures, perhaps time emerges as well. The idea remains speculative, yet it is increasingly discussed within theoretical physics. And if true, the implications are enormous. Because if time is emergent, then causality may emerge alongside it. The speed of light barrier may therefore be protecting not merely motion through spacetime, but the very framework from which spacetime arises, a deeper architecture hidden beneath ordinary experience. This possibility transforms the investigation. Once again, the question shifts, not how do we travel faster than light, but what would reality become if we could? Imagine removing the rules governing grammar from a language. Words remain, sounds remain, communication collapses. Perhaps causality plays a similar role within existence. Perhaps it is not an arbitrary restriction, but a prerequisite for meaningful structure, a requirement for coherent histories, a foundation upon which complexity depends. If so, then the speed limit begins to resemble something unexpected, not a prison, a stabilizer, a load-bearing component of reality. Yet certainty remains elusive, because physics contains another mystery lurking nearby, a mystery that may eventually overturn many current assumptions. The quest for a theory uniting quantum mechanics and gravity. For decades, physicists have searched for this missing framework, a theory capable of describing the smallest scales and the largest scales simultaneously. A theory of quantum gravity. No complete solution exists, not yet. But many researchers suspect the answer will fundamentally reshape humanity's understanding of space-time, information, and causality. Perhaps the speed of light barrier will look different within that framework. Perhaps wormholes will acquire new meaning. Perhaps entirely new possibilities will emerge. Or perhaps the limit will appear even more fundamental than it does today. Nobody knows. That uncertainty is important because it reminds us how incomplete our understanding remains. Despite extraordinary advances, humanity still lacks a complete description of reality. The deepest layer remains hidden, buried beneath successful theories, waiting. And this is where the investigation reaches a crucial turning point. For nearly a century, Scientists have asked whether anything can travel faster than light. Yet another possibility now demands attention. What if the question itself is misleading? What if the true mystery is not what lies beyond the speed of light, but why reality contains such a boundary in the first place? Because the closer researchers look, the less arbitrary the barrier appears, and the more it resembles a fundamental feature woven into the architecture of existence itself. The answer seemed near. Yet the next discovery would reveal just how much remained hidden beneath the surface. There is a peculiar pattern that appears throughout the history of science. Humanity discovers a boundary. We assume it is temporary, a challenge waiting to be overcome. Then, years later, we realize the boundary was never merely an obstacle. It was a clue. The horizon at sea once seemed like the edge of the world. Later, it became evidence that Earth was curved. The motions of planets once seemed chaotic. Later, they revealed hidden laws governing gravity. Again and again, limits transformed into revelations. And by the 21st century, some physicists began wondering whether the speed of light belonged to the same category. Perhaps it was not simply a restriction. Perhaps it was telling us something profound about the structure of reality. The evidence supporting this suspicion came from an unexpected direction, not astronomy, not particle accelerators, information theory. At first glance, information sounds less fundamental than matter or energy. After all, stars seem real. Galaxies seem real. Black holes seem real. Information feels abstract, almost secondary. Yet modern physics increasingly points toward a different conclusion. Information may be one of the deepest ingredients of existence. The clue emerged repeatedly. Quantum mechanics revolves around information. Black hole paradoxes revolve around information. Entanglement revolves around information. Even the observable universe is defined by informational limits imposed by the speed of light. Again and again, information occupied the center of the mystery. Eventually, some researchers proposed a radical shift in perspective. Instead of viewing the speed of light as the maximum velocity of objects, perhaps it should be viewed as the maximum velocity of information. The distinction sounds subtle. It isn't. Because objects are merely carriers. Information is the cargo. And in physics, the cargo matters more than the vehicle. Imagine a postal network. The important question is not how fast the trucks move. The important question is how quickly messages can spread. The trucks exist to transport information. Similarly, light may simply be nature's preferred messenger. The speed limit governs communication itself. Once viewed through this lens, many puzzles begin aligning. Causality depends upon information. Knowledge depends upon information. Observation depends upon information. Reality as we experience it depends upon information. The barrier appears less arbitrary, more necessary. Then another discovery complicated everything. Because researchers investigating black holes uncovered a relationship that seemed almost impossible, a relationship between gravity and information. For decades, gravity and quantum mechanics resisted unification. The two frameworks described reality brilliantly within their own domains, yet attempts to combine them generated contradictions. The mismatch became one of the greatest unsolved problems in physics. Then, certain theoretical breakthroughs suggested an unexpected possibility. Gravity itself might emerge from informational processes, not unlike temperature emerging from molecular motion. Temperature feels fundamental, yet it arises from deeper activity beneath the surface. Perhaps gravity behaves similarly. Perhaps space-time itself emerges from information. The proposal remains controversial, incomplete, actively debated, yet it possesses remarkable explanatory power, and if correct, the implications are staggering, because it means the stage upon which reality unfolds may not be fundamental. The stage may be generated, constructed, emergent, like an image appearing on a screen. The image feels real, yet its true origin lies elsewhere. The investigation had now reached a startling conclusion. The mystery was no longer primarily about faster-than-light travel. It was about the architecture from which space, time, and motion arise. And once that realization takes hold, a haunting possibility emerges. Perhaps there is no meaningful beyond the speed of light, at least not in the way people imagine. Consider a two-dimensional character living inside a drawing. The character wonders what exists beyond the edge of the page. The question sounds reasonable from their perspective, yet the deeper reality exists in a completely different dimension. The answer does not lie farther along the page. It lies outside the framework entirely. Some physicists suspect humanity may face a similar situation. We imagine moving beyond the speed of light because we remain trapped within familiar concepts of distance and motion. But perhaps the deeper layer of reality operates according to principles where those concepts no longer apply. This idea remains speculative, yet it keeps resurfacing in different forms. Quantum gravity, holography, emergent spacetime, information-based models of reality. Again and again, the same suggestion appears. Space may not be fundamental. Time may not be fundamental. Distance may not be fundamental. If so, then the speed limit may be less like a wall and more like a property of the emergent world we inhabit, a rule governing the surface, not necessarily the depths beneath it. For a moment, this perspective seems to resolve the mystery. The barrier becomes understandable. The puzzle dissolves. Case closed. But this would become perhaps the largest false ending of all, because the solution creates a question far more profound than the original mystery. If space and time emerge from something deeper, what is that deeper thing? Nobody knows. Not definitively. Researchers possess clues, mathematical frameworks, promising theories, but no complete answer. The deepest layer remains hidden, and that uncertainty matters because it reminds us that modern physics remains unfinished. Humanity stands in a peculiar position. We have mapped galaxies, detected gravitational waves, observed black holes, measured the age of the universe. Yet we still do not fully understand the stage upon which all those phenomena occur. The closer we approach the foundations, the more mysterious reality becomes. And nowhere is that mystery more apparent than in the speed of light barrier, a constant discovered through observations of distant moons, a number appearing throughout the laws of nature, a limit governing information causality and observation, a boundary that increasingly resembles a cornerstone of existence itself. Yet one crucial question remained. Suppose humanity never exceeds light speed. Suppose no loopholes exist. Suppose the barrier truly is absolute. What would that mean for our future among the stars? The answer forces the investigation away from physics alone, toward civilization, toward exploration, toward humanity's place in the cosmos. And there another mystery waits. For centuries the stars felt close, not physically close, emotionally close. They filled the night sky. They appeared reachable. Ancient civilizations built myths around them. Sailors navigated by them. Dreamers imagined visiting them. The distances remained abstract. Even after astronomy revealed their true nature, human intuition struggled to keep pace. A star is a point of light. How far away can a point of light really be? The answer, it turned out, was almost beyond comprehension. And nowhere does the speed of light barrier feel more real than when humanity begins calculating the journey. Take the nearest star system beyond our own, Alpha Centauri. From Earth it appears as a modest point in the southern sky, unremarkable, silent. Yet its light requires more than 4 years to reach us. Every photon arriving tonight began its journey years ago. Every observation is delayed. Every image is history. Now imagine traveling there. Modern spacecraft would require tens of thousands of years. Even the fastest probes humanity has ever launched barely begin to dent the distance. The challenge is staggering. And Alpha Centauri is merely our nearest stellar neighbor. Beyond it lie hundreds of billions of stars within the Milky Way. Beyond the Milky Way lie hundreds of billions of galaxies. The scale becomes almost impossible to visualize. Imagine shrinking Earth to the size of a grain of sand. The solar system would still occupy a vast area. The nearest stars would remain astonishingly distant. Galaxies would become separated by continents. The universe resists compression into human intuition, and the speed of light defines every journey through it. At first glance, this seems discouraging, perhaps even tragic. Humanity appears trapped, confined to a tiny corner of an unimaginably vast cosmos. Many people interpret the speed limit this way, as a prison, a cosmic restriction imposed upon an ambitious species. But history suggests a more complicated picture, because every major expansion of human horizons initially appeared impossible. Crossing oceans seemed impossible. Flying seemed impossible. Walking on the moon seemed impossible. Each challenge eventually yielded to innovation. Naturally, many scientists and engineers continue searching for pathways to the stars, not because faster-than-light travel is known to be possible, because the consequences would be transformative if it were. Imagine a civilization capable of crossing interstellar distances in weeks. The Milky Way would shrink dramatically. Separate worlds could exchange culture, knowledge, resources. History itself would change. The galaxy would become interconnected, not unlike Earth after the advent of rapid communication and transportation. The dream remains powerful, yet reality continues imposing constraints. Generation ships, cryogenic travel, relativistic spacecraft, laser-propelled probes. Each concept attempts to navigate the barrier rather than eliminate it, and each reveals something important. Humanity may not need faster-than-light travel to become an interstellar civilization. The process may simply require patience on scales unfamiliar to modern societies. This realization introduces a fascinating perspective shift. Perhaps the true challenge is not physics. Perhaps it is psychology. Humans evolved within lifetimes measured in decades. Civilizations rarely think in terms of millennia, yet the cosmos operates on vastly larger scales. Stars live for billions of years. Galaxies evolve over hundreds of millions. The universe itself has existed for nearly 14 billion years. Against that backdrop, human impatience appears remarkably local, remarkably temporary. Still, the temptation to circumvent the barrier remains, because the distances are so immense, and because the mystery itself refuses to fade. Every generation asks the same question. Surely there must be a way. Surely some loophole remains hidden. Perhaps. Yet another possibility deserves consideration. What if the speed limit performs a deeper function? What if it shapes the character of the universe itself? Imagine a cosmos without communication delays. Every event influences every other event instantaneously. Distances lose significance. Locality disappears. Cause and effect become profoundly different. The universe would not merely become faster, it would become structurally different, perhaps unrecognizable. This possibility is often overlooked. People naturally focus on what faster-than-light travel would allow. Few consider what it would eliminate. The speed limit creates separation. Separation creates individuality. Regions of the universe develop independently. Histories diverge. Complex structures emerge. The cosmos acquires texture. A universe without informational delays might behave very differently. Perhaps less coherently. Perhaps less stably. Nobody knows. Yet the possibility reinforces a recurring theme. The barrier appears deeply integrated into reality, not superficial, not arbitrary, integrated. Then another intriguing question emerges. If the speed limit is so fundamental, why does its value possess the specific magnitude we observe? Why approximately 299,792 kilometers per second? Why not twice that value? Why not half? Why not infinitely fast? The question sounds simple. It isn't. Because modern physics currently lacks a deeper explanation. The number appears throughout nature. It connects electromagnetism, relativity, spacetime geometry. Yet nobody knows why reality chose that specific value, or whether the question itself is meaningful. Perhaps future theories will explain it. Perhaps they won't. The uncertainty remains, and that uncertainty points toward an important truth. Even after more than a century of investigation, the speed of light remains partly mysterious. Not mysterious because we cannot measure it. We can. Not mysterious because we cannot use it. We do. Mysterious because we still do not fully understand why reality is organized around it. The barrier has transformed from a practical limitation into a philosophical clue, a clue pointing toward deeper layers of structure hidden beneath everyday experience. And as the investigation approaches its final stages, one possibility becomes increasingly difficult to ignore. Perhaps the ultimate significance of the speed of light barrier has less to do with travel and more to do with knowledge itself, because every horizon created by light defines a horizon of understanding, and those horizons may reveal something profound about humanity's place in the universe. Every civilization lives inside a horizon. The horizon may be physical, geographical, technological, intellectual, but it is always there. Ancient sailors lived within the horizon of the sea. Everything beyond it belonged to speculation, myth, rumor, possibility. Then ships crossed the boundary. The world expanded. New horizons appeared. The pattern repeated throughout history. Microscopes revealed hidden worlds within cells. Telescopes revealed hidden worlds among the stars. Mathematics revealed hidden worlds inside equations. Each breakthrough expanded humanity's sphere of knowledge. Yet every expansion also revealed something unsettling. The unknown grows faster than the known. The farther we see, the more darkness becomes visible beyond the edge. And nowhere is this paradox more apparent than in modern cosmology. Because the speed of light does not merely define how far we can travel, it defines how far we can know. The distinction matters enormously. Imagine standing in a vast library. Every shelf beyond a certain distance becomes invisible, not because the books are absent, because information from those books cannot reach you. The library continues. Knowledge exists. Access does not. This is remarkably similar to humanity's situation within the cosmos. The observable universe is not necessarily the entire universe. It is simply the region from which information has had time to arrive, a visible island within a potentially much larger reality, perhaps infinitely larger. Nobody knows. The uncertainty itself is extraordinary. Modern astronomy has revealed billions of galaxies, each containing billions of stars. Yet all of them together may represent only a tiny fraction of existence, a local sample, a small illuminated region surrounded by immeasurable darkness. This realization creates a strange tension. Humanity knows more about the universe than any previous civilization, yet we are increasingly aware of how much remains inaccessible. Knowledge expands. Ignorance expands with it. The speed of light barrier sits precisely at that intersection, a boundary separating observation from speculation, evidence from imagination, what can be tested from what can merely be contemplated. Then comes an even stranger realization. Everything you know about the cosmos is old, not metaphorically, literally. The moon you see is approximately 1 second old. The sun is roughly 8 minutes old. Nearby stars are years old. Distant galaxies are millions or billions of years old. Some of the most ancient light observed by the James Webb Space Telescope began traveling toward us long before Earth existed. Astronomy is unlike any other science. Geologists study ancient rocks. Archaeologists study ancient civilizations. Astronomers study ancient reality itself. Every observation arrives from the past. Every image is a historical document. Every photon carries a timestamp. The universe we observe is therefore not the universe as it exists now. It is the universe as it once was, a vast collection of delayed messages arriving from every direction. The thought is difficult to fully absorb. No observer can ever see the cosmos in its present state. The speed limit prevents it. Reality reveals itself only through memories, only through echoes, only through traces. And this transforms the investigation yet again, because it suggests that the speed of light does more than constrain motion. It structures perception itself. The barrier determines what can be experienced, what can be observed, what can be known. In a profound sense, it shapes consciousness, at least consciousness as it exists within a physical universe. Then another perspective emerges, one that feels almost philosophical. Imagine a universe where information traveled infinitely fast, no delays, no horizons, no observational past. Everything, everywhere, instantly available. Would such a universe even possess meaningful locality? Would separate regions truly exist? Would independent histories emerge? The question remains speculative, yet it highlights something important. The speed limit creates structure. It partitions reality into neighborhoods, histories, Perspectives. Without those separations, existence itself might become fundamentally different. This possibility reinforces a growing suspicion among physicists. The barrier may not be an accidental feature. It may be a prerequisite, a condition necessary for the emergence of complexity, for the emergence of observers, perhaps even for the emergence of coherent reality. Nobody can yet prove such claims, yet the clues continue accumulating. Information theory, relativity, quantum mechanics, cosmology. Again and again the same conclusion appears. The speed of light occupies an unusually central position within the architecture of existence. Then comes perhaps the most unsettling implication of all. There may be questions humanity can never answer. Not because we lack intelligence, not because technology fails, because information itself remains inaccessible. Certain regions lie beyond observation. Certain events remain forever hidden. Certain truths may never enter our causal horizon. Science rarely emphasizes this possibility. Science is often associated with limitless discovery, endless progress, infinite expansion of knowledge, and to a remarkable degree, that optimism has been justified. Yet every discipline eventually encounters boundaries, and the speed of light barrier may represent one of the deepest. A reminder that reality does not owe complete transparency to its observers. Some mysteries may remain unresolved, not temporarily, permanently. That possibility feels uncomfortable, yet it also carries a certain beauty, because mystery survives, wonder survives, the unknown survives, the universe retains depth, and as the investigation approaches its conclusion, a final question begins to emerge. Suppose humanity never crosses the speed of light barrier. Suppose the limit remains absolute forever. Would that make the universe smaller, or would it reveal something more profound about what exploration truly means? The answer may have less to do with physics than with perspective, and it would force scientists to confront one of the oldest questions ever asked. Not what lies beyond the speed of light, but what it means to exist within a universe that has limits at all. At some point, every investigation changes. The evidence accumulates. The clues connect. The original question remains important, but a deeper question emerges beneath it. That moment has now arrived. Because the mystery was never simply about moving faster than light. At first, it seemed that way. A technological challenge, a transportation problem, a cosmic speed limit waiting to be broken. Yet every path we followed led somewhere unexpected. Tachyons led to causality. Warp drives led to spacetime. Wormholes led to time travel. Entanglement led to information. Cosmology led to horizons. Again and again, the investigation moved away from motion and towards something deeper. Structure. Order. Reality itself. And perhaps that shift reveals the true significance of the speed of light barrier. Consider what would happen if the limit vanished tomorrow. Not increased, not modified. Removed entirely. Information could travel instantly. Every point in the universe could influence every other point without delay. Cause and effect would become profoundly different. The very meaning of locality might disappear. The cosmos would cease to resemble the universe we know. This thought experiment highlights something crucial. The speed limit is not merely a restriction placed upon travelers. It is part of the framework that allows the universe to possess coherent structure, like the rules of grammar in a language, or the laws of harmony in music. The rules impose constraints, yet those constraints make complexity possible. Without them, meaning dissolves. Then another realization appears, one that many physicists find difficult to ignore. The speed of light is not simply fast. It is woven into the equations describing reality at every scale. Electromagnetism depends upon it. Relativity depends upon it. Quantum field theory depends upon it. Cosmology depends upon it. The constant appears repeatedly, like a signature hidden throughout a manuscript, a recurring clue pointing toward deeper unity. The more researchers study nature, the less accidental the number appears, and that observation raises a profound possibility. Perhaps the speed limit is not a feature of our universe. Perhaps it is a feature of any universe capable of sustaining consistent laws. The idea remains speculative, yet it has gained attention because of a remarkable pattern. Every successful physical theory seems to require limits on information propagation. Without such limits, causality becomes unstable. Prediction becomes difficult. Structure becomes fragile. Reality itself begins to lose coherence. The pattern is difficult to dismiss, and once seen, it appears everywhere. Imagine building a city. Roads require speed limits. Communication networks require bandwidth limits. Complex systems often depend upon constraints, not despite them, because of them. The universe may operate similarly. The speed of light barrier may represent one of the constraints from which cosmic order emerges. If so, then the barrier is not a prison. It is infrastructure, a foundational component supporting everything built upon it. This perspective creates a fascinating reversal. For more than a century, people have asked how to overcome the speed limit. Perhaps the deeper question is why the universe needs it. The answer remains incomplete. Yet evidence increasingly points toward information, causality, consistency, the preservation of meaningful histories. Then another clue appears, one hiding in plain sight. Every observer occupies a unique causal horizon. Every observer possesses access to a different portion of reality. No perspective contains everything. No viewpoint sees the entire universe. This fact often feels like a limitation, yet it may also be essential, because perspective itself depends upon separation. Individuality depends upon locality. Observers exist because information requires time to propagate. Without delays, distinctions blur, histories merge, experiences lose uniqueness. Again, the speed limit appears less like an obstacle and more like an organizing principle. Then comes an unsettling possibility. What if the ultimate answer lies beyond current physics entirely? History provides many precedents. Newton's gravity appeared complete until relativity arrived. Classical physics appeared complete until quantum mechanics arrived. Again and again, revolutionary frameworks transformed seemingly settled questions. The same may happen here. Future theories may reveal structures humanity cannot yet imagine. New dimensions, new informational architectures, new interpretations of space and time, possibilities currently hidden behind the limits of present understanding. The point is not that faster than light travel will necessarily become possible. The point is that certainty remains premature. The investigation remains unfinished. The final chapter has not been written, and that uncertainty matters, because uncertainty is often where discovery begins. The history of science is not a story of final answers. It is a story of expanding mysteries. Each generation solves certain puzzles and inherits larger ones. The speed of light barrier fits that pattern perfectly. What began as a measurement became a law. The law became a mystery. The mystery became a doorway into the foundations of reality. And now, standing near the edge of current knowledge, humanity faces an extraordinary situation. We understand more about the speed of light than any civilization in history. Yet we still do not fully understand why reality is organized around it. The clue remains visible. The meaning remains partly hidden, like an ancient inscription whose symbols are clear, but whose language is not yet fully deciphered. And the closer we examine that inscription, the larger the mystery becomes. Because the investigation is no longer asking what happens beyond the speed of light, it is beginning to ask what lies beyond our understanding of reality itself. There is a moment that arrives in every great investigation, a moment when the evidence no longer points toward a single answer. Instead, it points toward a boundary, a place where knowledge begins to fade, where certainty gives way to possibility, where science transitions from explanation to exploration. The mystery of the speed of light has now reached that boundary, and what lies beyond it is not a destination, it is a question. For more than a century, physicists have attempted to understand why reality contains a universal speed limit. And first the task appeared straightforward. Measure the limit, describe it mathematically, apply it to nature. Problem solved. Yet every attempt to explain the limit completely has uncovered deeper layers beneath it. Relativity revealed that space and time are intertwined. Quantum mechanics revealed that information behaves in profoundly unfamiliar ways. Black holes revealed hidden relationships between gravity and entropy. Cosmology revealed horizons defining what can be known. Each breakthrough brought humanity closer to understanding, and simultaneously revealed how incomplete that understanding remains. The pattern is striking, almost uncanny. The closer science approaches the foundations of reality, the more those foundations begin to resemble mysteries. Not because the evidence disappears, because the evidence becomes richer than the concepts used to describe it. This has happened before. Ancient astronomers observed planetary motion long before they understood gravity. Early physicists observed electricity long before they understood electromagnetism. Today, humanity may be observing clues about reality that future generations will interpret very differently. The speed of light barrier could be one of those clues, a phenomenon understood operationally but not yet understood fundamentally. Then comes a realization that many researchers find both exciting and unsettling. The universe appears remarkably comprehensible. Pause and consider that for a moment. The laws governing galaxies also govern atoms. The mathematics describing distant quasars also describes laboratory experiments. Patterns repeat across scales. Order emerges from complexity. This coherence is extraordinary. There is no obvious reason reality should be understandable, and yet it is. At least partially. The speed of light plays a central role in that coherence. It synchronizes the structure of spacetime. It governs causal relationships. It limits informational propagation. It helps create a universe capable of consistent behavior. Remove it, and much of modern physics collapses. Keep it, and a remarkable degree of order emerges. This observation has led some scientists toward a provocative idea. Perhaps the constants of nature are not arbitrary. Perhaps they are interconnected expressions of deeper principles still waiting to be discovered. The speed of light may be one visible fragment of a hidden framework, like a mountain peak protruding above clouds. The visible portion is real. The larger structure remains concealed. If that analogy is correct, then humanity has spent the last century studying the peak while only beginning to glimpse the mountain. The thought is humbling, because it suggests that even our most successful theories may represent intermediate steps, rather than final truths. Then another perspective emerges, one borrowed from history. Imagine speaking with an astronomer from the 15th century. You describe galaxies, black holes, relativity, quantum mechanics, the age of the universe. Most of these concepts would seem incomprehensible, not because the astronomer lacks intelligence, because the necessary conceptual framework does not yet exist. Now reverse the thought experiment. Imagine a physicist living 500 years from now. Perhaps they possess theories that make our current understanding appear similarly incomplete. Perhaps concepts that seem mysterious today will eventually appear obvious. Perhaps entirely new mysteries will replace them. Nobody knows. And that uncertainty is important because it reminds us that science is not a collection of final answers. It is a process, a journey, an expanding map of reality. The speed of light barrier occupies a fascinating position on that map. It is simultaneously understood and mysterious, measured and unexplained, fundamental and possibly emergent. The duality itself is revealing. Then comes perhaps the most significant clue uncovered during the entire investigation. Every route beyond the speed of light eventually transformed into a question about information, not motion, not engines, not spacecraft. Information, again and again. Relativity protected informational order. Entanglement constrained informational transfer. Black holes challenged informational preservation. Cosmic horizons restricted informational access. The pattern became overwhelming. Whatever the ultimate explanation may be, information appears deeply involved. Some physicists even suspect that information is more fundamental than matter itself, more fundamental than space, perhaps even more fundamental than time. The idea remains controversial, yet it reflects a growing shift in scientific thinking. Reality may not be built from objects. Reality may be built from relationships, connections, information. If so, the speed of light barrier acquires an entirely new meaning. It becomes a rule governing the flow of existence itself. Not merely the movement of particles through space, the movement of information through reality. And that possibility changes everything, because once the mystery reaches this level, it can no longer be contained within physics alone. It begins touching philosophy, consciousness, knowledge, observation, the nature of existence. The investigation started with a simple question: what happens beyond the speed of light? Now it is approaching a far stranger one. What kind of reality requires a speed limit in the first place? The answer remains hidden. But the final stage of the journey is about to reveal why that hidden answer matters so much, not only for science, but for humanity itself. Throughout history, humanity has repeatedly mistaken scale for significance. We assumed Earth occupied the center of creation. It didn't. We assumed the solar system was vast. It wasn't. We assumed the Milky Way contained everything. It didn't. Again and again, expanding knowledge forced us to confront a humbling reality. The universe is larger than expected, older than expected, stranger than expected. And the mystery of the speed of light ultimately belongs to that tradition, because beneath all the equations, experiments, and theories lies a deeper lesson. A lesson about limits. Human beings have a complicated relationship with limits. We celebrate overcoming them. Crossing oceans, climbing mountains, breaking records, expanding frontiers. Progress often appears to be a story of barriers falling. Naturally, many people assume the speed of light barrier must eventually suffer the same fate. Why should this limit be different? Why should this wall remain standing when so many others have fallen? It is a reasonable question, yet history offers another perspective. Not every limit exists to be overcome. Some limits define the system itself. A chessboard contains boundaries. Remove them, and the game disappears. Language contains grammar. Remove it, and communication collapses. The constraints are not obstacles to the activity. They make the activity possible. The speed of light barrier may belong to this category, not a challenge waiting to be defeated, a condition enabling reality as we know it. This possibility becomes increasingly difficult to ignore as the evidence accumulates. Again and again, the speed limit appears connected to causality, information, observation, structure. The universe seems organized around it, almost built upon it, and that realization changes the emotional character of the mystery. At first, the barrier feels restrictive, disappointing, a reminder of what humanity cannot do. Yet viewed differently, it becomes something else, a clue, a piece of architecture, evidence that reality possesses deeper order. Imagine discovering a hidden support beam inside an ancient cathedral. At first, it looks like an obstruction. Then you realize the entire structure depends upon it. The beam is not preventing the cathedral from standing. It is the reason the cathedral stands at all. The speed of light may play a similar role within the cosmos. Then comes another perspective shift, one perhaps even more profound. The barrier does not merely limit travel, it creates perspective. Because information requires time to propagate, every observer experiences a unique view of reality, a unique causal horizon, a unique history. No observer sees everything. No observer occupies a privileged position. This fact is often presented as a limitation, yet it may also be one of the reasons complexity exists. A universe in which everything instantly influences everything else may not permit the same richness of structure. Local histories matter because locality exists. Individual stories matter because separation exists. The speed limit helps create that separation, and separation creates diversity, complexity, novelty, evolution. Civilizations, observers. The possibility is difficult to prove, yet it fits a recurring pattern. Constraints often enable creativity rather than suppress it. Then another realization emerges, one touching the relationship between science and mystery itself. Many people imagine science as a process that gradually eliminates mystery, a machine converting unknowns into knowns. There is truth in that description, yet it is incomplete. Because science also creates new mysteries. Every major discovery expands the frontier of ignorance. Every answer reveals questions that previously could not even be asked. The speed of light barrier illustrates this perfectly. A simple measurement evolved into one of the deepest mysteries in modern physics. The more humanity learned, the larger the question became, not smaller. larger. That pattern may itself contain an important lesson. Reality is not a puzzle with a final piece waiting to be inserted. Reality may be an infinite landscape of nested mysteries. Each horizon conceals another. Each solution reveals deeper structure. The journey never truly ends. And perhaps that is exactly as it should be, because mystery is not the opposite of knowledge. Mystery is what makes knowledge meaningful. Without unanswered questions, exploration would cease. Without uncertainty, discovery would lose purpose. Without horizons, there would be nowhere left to travel, even intellectually. Then comes a final, haunting possibility. Suppose humanity eventually develops technologies beyond anything currently imagined. Suppose future civilizations spread among the stars. Suppose they manipulate space-time, harness energies dwarfing entire planets, perhaps even entire galaxies. Would the mystery disappear? Maybe not. The history of science suggests otherwise. Every expansion of capability reveals larger unknowns. The horizon moves. The questions evolve. The mystery survives. Which means that even the most advanced civilization imaginable may still confront limits, still encounter horizons, still gaze toward regions beyond understanding, still wonder what lies hidden beneath reality. And that observation brings us unexpectedly close to the deepest implication of the entire investigation. The speed of light barrier is not merely a fact about physics, it is a reminder that existence contains boundaries. That knowledge has horizons. That mystery remains woven into the fabric of the cosmos. The question is no longer whether something exists beyond the speed of light. The question is what that possibility teaches us about our place within reality. And the answer may be more profound than any technology humanity could ever build. There is a tendency, especially in modern civilization, to imagine that knowledge accumulates in a straight line. Yesterday, we knew less. Tomorrow, we will know more. Eventually, enough discoveries will solve the remaining mysteries. The darkness will retreat. The map will be complete. The story will end. It is an appealing vision, and in many ways history encourages it. Humanity has achieved extraordinary things. We have decoded the genetic language of life, walked on another world, detected ripples in space-time, photographed the shadow of a black hole, measured the age of the cosmos. Compared with our ancestors, we inhabit an age of astonishing understanding. Yet standing at the edge of the speed of light mystery reveals something different. Knowledge does not expand like a line. It expands like a circle. As the circle grows larger, its boundary with the unknown grows larger too. The frontier never disappears. It becomes more extensive, and perhaps nowhere is that more evident than in modern physics. Consider the situation humanity finds itself in today. We possess two extraordinarily successful descriptions of reality. Quantum mechanics describes the microscopic world with astonishing accuracy. Relativity describes gravity, space-time, and the large-scale structure of the cosmos with equal success. Both theories work. Both have survived countless experimental tests. Yet they remain incomplete. When pushed to their deepest limits, they refuse to fit together cleanly. The foundations remain unfinished. The most successful scientific framework in history still contains gaps, still contains mysteries, still contains unanswered questions. The speed of light barrier sits directly inside that unfinished territory. It is measured with extraordinary precision. Its consequences are understood with remarkable accuracy. Yet its deepest meaning remains uncertain. A constant, a limit, a clue, an unanswered question, all at once. This combination is unusual, and it reveals something important about the nature of discovery. Science often begins by answering questions. Eventually, the answers become clues to larger mysteries. The speed of light followed exactly that path. What is its speed? Measured. Why is it constant? Partially explained. Why does reality require such a limit? Still uncertain. What deeper structure creates it? Unknown. The investigation never truly ends. It evolves. Then comes perhaps the most humbling realization of all. The universe is under no obligation to be understandable. There is no cosmic rule requiring reality to make sense to human minds. The laws of nature were not designed for our convenience. The cosmos existed for billions of years before intelligence emerged on Earth, and yet somehow human beings can comprehend portions of it. We can derive equations describing stars, Predict the behavior of black holes. Model the evolution of galaxies. That achievement is extraordinary. Not because we know everything, because we know anything at all. Imagine a collection of atoms arranging themselves into a conscious observer. That observer then begins decoding the laws governing the universe from which those atoms emerged. The situation borders on the miraculous, and the speed of light barrier represents one of the clearest examples, a feature woven into every observation, every signal, every glimpse of the cosmos, a boundary so familiar that it often disappears into the background. Yet when examined carefully, it reveals profound truths about information causality and reality itself. Then another perspective emerges, one less scientific, more existential. Every human life unfolds within limits. Time is limited. Knowledge is limited. Perspective is limited. No individual experiences everything. No civilization learns everything. No observer sees the entire cosmos. At first glance, these limitations appear unfortunate, but perhaps they are also what give meaning to experience. Stories matter because they are finite. Moments matter because they pass. Exploration matters because the destination is not already known. In a curious way, limits create significance. The speed of light barrier may participate in that same pattern, not merely restricting possibility, helping define it. The idea cannot be proven experimentally, yet it resonates with a recurring theme uncovered throughout this investigation. Boundaries often serve purposes that are not immediately obvious. Again and again, apparent restrictions reveal deeper functions. Again and again, walls become clues. Then the final horizon appears. Not a scientific horizon, a philosophical one. Suppose humanity eventually understands the speed of light barrier completely. Suppose future theories explain its origin, its necessity, its role in reality. What then? Will the mystery end? History suggests otherwise. The answer will almost certainly generate new questions, new horizons, new unknowns, because every completed map reveals territories beyond its borders. Every discovery expands the frontier, and that frontier may be infinite, which means the deepest lesson of the speed of light mystery may not concern travel at all. It may concern humility, the recognition that understanding is always partial. That certainty is always provisional. That mystery remains an enduring feature of existence, not a flaw, a feature. And as the investigation approaches its final chapter, one realization becomes impossible to ignore. The question we started with has quietly transformed. We asked, what happens beyond the speed of light? Now we are confronting something much larger. What happens when human knowledge reaches its own horizon? The answer may reveal more about us than about the universe. In the beginning, the mystery seemed simple. There was a speed limit. Humanity wanted to know what existed beyond it. A familiar story, a boundary, a challenge, a frontier waiting to be crossed. For centuries, that is how we have understood progress. Find the horizon, move beyond it, repeat. Yet the investigation led somewhere unexpected, because every path beyond the speed of light eventually curved back toward deeper questions. Questions about time. Questions about information. Questions about causality. Questions about the architecture of reality itself. The farther we travelled, the less the mystery resembled a transportation problem, and the more it resembled a clue. A clue hidden in plain sight since the moment humanity first measured the speed of light. Consider everything the investigation uncovered. The universe allows extraordinary things. Black holes that distort space-time. Quantum entanglement connecting distant particles. Galaxies receding faster than light because space itself expands. Possible wormholes hidden within the equations of gravity. Possible warp geometries buried inside relativity. Again and again, reality proved stranger than intuition. Yet, despite all that strangeness, one pattern persisted. The speed limit endured. Every apparent loophole carried conditions, restrictions, complications. The deeper scientists looked, the more fundamental the barrier appeared. Not weaker, stronger, not accidental, necessary. Perhaps that conclusion will eventually change. Science has surprised humanity before. It will surprise humanity again. Future discoveries may reveal structures that today remain invisible. Future theories may transform our understanding of space-time. Future civilizations may possess concepts beyond anything we currently imagine. That possibility should never be dismissed. History repeatedly punishes certainty, yet uncertainty cuts both ways. It reminds us not only that current theories may be incomplete, it reminds us that some mysteries may be deeper than expected. The speed of light barrier appears to belong to that category, a mystery whose roots reach downward into the foundations of existence. And that realization changes the emotional meaning of the question, what lies beyond the speed of light? At first, the phrase evokes distance, distant stars, distant galaxies, remote frontiers. But after everything we have uncovered, the question feels different, because beyond may not refer to location at all. It may refer to understanding. The true frontier may not lie beyond some cosmic destination. It may lie beyond the conceptual framework humanity currently uses to interpret reality. This has happened before. Ancient astronomers could not discover relativity because the necessary concepts did not yet exist. 19th century physicists could not discover quantum mechanics because the conceptual tools were missing. Perhaps our own era faces a similar limitation. Perhaps the deepest layer of reality remains hidden not because evidence is absent, but because the correct questions have not yet been asked. The possibility is both frustrating and exhilarating. Frustrating because it means the mystery remains unresolved. Exhilarating because it means discovery remains possible. The story is not finished, and perhaps it never will be. Then comes one final perspective shift, one last scale expansion. Throughout this investigation, humanity occupied a peculiar position, small enough to be humbled by the cosmos, yet capable of understanding pieces of it. Tiny observers living on a planet orbiting an ordinary star inside an ordinary galaxy. And yet those observers learn to detect black holes, measure cosmic expansion, study the first moments after the Big Bang, trace the behavior of photons that have traveled billions of years. That achievement is remarkable, not because it produced complete understanding, because it produced any understanding at all. A collection of conscious beings emerged within the universe and began asking questions about the universe. The mystery of the speed of light is one expression of that larger story. The story of awareness confronting reality, of curiosity confronting uncertainty, of knowledge expanding toward horizons it can never fully eliminate. And perhaps that is the deepest lesson hidden beneath the entire investigation. The value of a mystery does not depend upon solving it completely. Some mysteries are valuable because they reveal how much remains unknown, because they remind us that reality is larger than our models, larger than our assumptions, larger than our certainty. The speed of light barrier has played that role for more than a century. A measured constant, a cosmic limit, a doorway into deeper questions, a reminder that every answer contains traces of larger mysteries waiting beneath it. So what really happens beyond the speed of light? The honest answer is that nobody knows. Not completely. Perhaps there are hidden structures beneath space-time. Perhaps information flows through layers of reality we have not yet discovered. Perhaps wormholes or warp geometries represent genuine possibilities. Perhaps causality itself prevents such paths from ever becoming real. Perhaps the barrier is fundamental. Perhaps it is emergent. Perhaps it is both. The evidence remains incomplete. The investigation remains open, and maybe that is exactly where it belongs. Because every generation inherits mysteries from the generations before it, and leaves mysteries for those who follow. The speed of light may be one of those enduring mysteries, a question passed forward through time, a clue waiting for future minds, a horizon that retreats as knowledge advances. And if that is true, then the real lesson may be this. The universe is not merely a collection of answers waiting to be discovered. It is a landscape of mysteries, some solved, some unsolved, some perhaps unsolvable. Yet every one of them invites us to look farther, think deeper, question more carefully, and continue the investigation. Perhaps one day humanity will uncover what truly lies beyond the speed of light. Or perhaps the greater discovery will be understanding why the question itself matters. Maybe the barrier is not the end of a journey. Maybe it is the beginning of a much larger one, and somewhere beyond the edge of our current understanding, hidden beneath the structure of space-time itself, the next clue may already be waiting. And as we come to the end of this journey, perhaps the most fascinating discovery isn't what lies beyond the speed of light. Perhaps it's the realization that every answer we uncover reveals an even larger mystery waiting in the darkness. If you enjoyed exploring these questions with me, consider subscribing and joining us for future investigations into the hidden corners of the universe. There are still ancient signals to trace, forgotten mysteries to uncover, and cosmic questions that may take generations to answer. And I'd love to hear your thoughts. If humanity could somehow travel beyond the speed of light, what do you think we would find first? A new frontier, a deeper layer of reality, or simply a larger mystery waiting beyond the horizon? Until next time, keep looking up. The universe is far stranger than it appears.